Hi class, we are on to chapter 8.4. This is the last section of chapter 8 that we're going to cover. This is plane curves and parametric equations. Parametric equations are basically us calling our two variables x and y two different functions, right? So x is defined by a function and y is defined by a function. So since our input and output variables are now defined by a function, we need a new input variable. Okay, so once we have two functions that work for our x and our y, we call our equation parameterized, right? We now have a parametric equation. Okay. So x is some function of t and y is some function of t. T generally stands for time, and as time progresses, our values of x change and our values of y change. Okay. So the curve that's created from a set of parametric equations is called a parametric curve. Okay. The only difference between a regular curve or function and a parametric curve is that a parametric curve has a direction. There's a certain direction that it flows because time only moves in one direction. So as time moves forward, our function will be created in a direction. Okay, so let's start an example. So let's sketch and identify the curve that's defined by the parametric equations x equals t squared minus 2t and y equals t plus 1. So the easiest way to do this, not the easiest, the initial way that we're going to do this is by looking at various values of t and finding the x values and the y values for those values of t, right? Pretty standard. So we're going to make a table of values. We'll count t. We can start at 0. Or we can start at negative values. It doesn't really matter. In this case, we're actually going to start with a couple of negative values and work our way forward. So when t is negative 2, I'm going to get 4 plus 4, right? So that'll be an 8. And then my y will be negative 2 plus 1. So that'll be a negative 1. So my point when time is negative 2 is the point 8, negative 1. Negative 1 will give me the same thing. This will be 1 plus 2, so that'll be 3 for x, and this will be 0. So my point is 3, 0. When I plug in 0, x is 0, and this is 1. When I plug in 1, I get 1 minus 2, or negative 1, and this becomes 2. Okay, so there's my point. When I plug in 2, I have 4 minus 4, so this becomes 0 again, and then this becomes 3. 9 minus 6 is 3, and then this becomes 4. This is 16 minus 8, so I have 8 again, and then when I plug in here, I have 5. Okay. Notice what's going on here. So my t is counting up, and notice what happened with my x values. I got 8 and 8, 3 and 3, 0 and 0, negative 1, right? So that looks like a parabola, right? Although that's not the output values that are doing it, it's the input values, right? So let's go ahead and look what this looks like as a graph. So we're going to plot these in order. First with 8, negative 1, and then we're going to go to 3, 0, and 0, 1, and so forth. So we're going to plot these in order because this is the direction that the curve is going. So my first point was 8, negative 1, and that was when I had t was negative 2. My next value was 3, 0, and then 0, 1. So t equals negative 1 was at 3, 0. My next value was at 0, 1, and that was when t was 0. Then I had negative 1, 2 for t equals 1. Then I was at 0, 3 for t equals 2, and 3, 4, and then 8, 5, I believe. Okay, so we actually have a rotated parabola here. Okay, and it has a direction, right? What's the direction it goes in? It goes in this direction. Okay, oops, as we can see, right? So as time goes, we have a direction. So this is really, really useful when we're doing things like modeling a particle flow through space, right? As a particle goes through space, it goes in a direction, right? This could even be an orbit or a trajectory of a spacecraft or a satellite, right? We come in and then it makes its parabolic turn, and it has a direction. It flows from left to right, and then it goes from from right to left and then left to right. So we like to use parametric equations. A lot of times it makes things easier to analyze. Sometimes it doesn't, but it's a nice, useful model that we can use. Okay. The equation for this parametric equation is x equals y minus 1, y minus 3, which should make sense because it's kind of like swapping out my input and output values. It's really just a parabola with zeros of 1 and 3, but the zeros are not on the x-axis, they're on the y-axis. So it'll be equation as x equals something because this is not a standard function, right? This is a, I guess you could think of it as an inverse function or a rotated function. So I have y minus 1 and y minus 3 as my zeros. So this would be my standard equation for this equation, okay? Now, a lot of times we would like to know how to find out what the equation is without having to graph the equation parametrically and then look at it and say, let me see if I can find a function that works for it. Because what if this was a really, really ugly equation? Maybe it wasn't this sideways parabola. Maybe it was something else that's very, very difficult to figure out exactly what the equation is. Well, there's a way for us to go from a parametric equation into our standard Cartesian rectangular coordinate equation, right? And so the way that we do that is we recognize that x and y, okay, are two functions with the same variable, right? X is a function of t and y is a function of t. So really what we need to do is we take one of these things and we solve for t and then plug it into the other. So we really just think about it as a system of equations in two variables, okay? So I'm going to take this, I'm going to solve one of them for t. The easiest one to solve for t is y, right? So all I have to do is subtract 1. Not only that, but if I try to solve x for t, I'm going to get two different values. And so when I plug that into y, I got to plug in two different values, okay? So the easiest way to do this is to solve for t using the y, because it's the simplest equation. I'm going to take this y minus 1 and I'm going to plug it in to my x. So everywhere I see t, I replace it with y minus 1. Okay. So y minus 1 squared minus 2 times y minus 1. So it's not quite our equation yet, but if we go ahead and multiply this out, right? So we expand this, distribute this negative 2, combine my like terms, and then it's easy to see that this actually factors to the same thing, right? Negative 1 and negative 3 gives me the negative 4. Negative 1 times negative 3 gives me the positive 3. And it factors to the same equation. Okay. So there are a few very common parametric equations. We'll see these throughout the textbook as we go through the course, especially in chapter 11. We'll see quite a few different parametric equations. And in chapter 9 as well, when we talk about vectors. So a few common ones are x equals cosine of t and y equals sine of t. This you've actually been exposed to already, right? We know that when x is cosine and y is sine, this creates a circle, right? The unit circle. Okay, so we go from 0 to 2 pi. When x is a function, cosine, and y is sine, we know that this gives a circle of radius 1. Okay, because that's how we formulated all of our trig explorations. An easy way to see that is notice that if I take x and I square it, and I take y and I square it, x squared plus y squared, that's cosine squared plus sine squared, which we know is 1. So we have the equation x squared plus y squared equals 1, the unit circle. Okay. Now let's say that we multiply cosine times r and y times r. Well, now we're expanding that circle to now have a radius of r. So it's a circle of radius r. So we're actually going to study these two parametric equations, this parametric equation, the x r cosine t and y r sine t, in depth. We've actually done it already in this section because that's how we go from polar coordinates to our rectangular coordinates. But we're going to study this a lot later as well. Okay. So if I have a cosine of t and y equals b sine of t. So here I'm expanding my x by one value and I'm expanding my b by a different value. That's going to give me an oblong circle, and an oblong circle is just an ellipse, right? So it's basically a circle that's not equally spaced out by a radius. Okay. So the interval for t in our previous example determines how many times around the circle we're going to go. So for instance, if I have 0 to 2 pi for this unit circle, then I only go around once. If I have a larger domain for t, well, then I'm going to go around more than once. Okay. Same thing here, which is also a circle, right? Same thing here for an ellipse. Okay. I can move around an ellipse multiple times if I'm going more than once around the circle, right? So for instance, it was 0 to 3 pi, then we would go around 1.5 times. Okay. The next common one is the equation of a line, right? So we can actually make the equation of a line that goes through a specific point and has a slope that we want it, right? So if we want to take the equation y equals 2x plus 1, right? We know that that equation has a slope of 2, and it goes through, I don't know, we can pick any point. So if we want to turn that into a parametric equation, we understand that 2 is 2 over 1. So x would be t plus whatever point 2x plus 1 goes through that I decided to choose. And the y function would be 2t, right, because it's 2 over 1, plus the y value of whatever function I needed. I need my function to go through. Okay, so there's lots of ways to parameterize an equation. An easy way is to just say, hey, let x equals t, and then my y equals my function, right? So that's the easiest way to do a parameterization. Nothing really interesting comes out from that. It's kind of like the cheap way to do it, but it's a method of parameterizing, right? So again, parametric equations are very, very useful in describing particles through space as time progresses.